All right, welcome class. Today we're going to be talking about two ethics cases. The first one being planetary protection, and then we'll have a discussion that is not going to be recorded. And then we will have a primer on human exploration in space as it pertains to low Earth orbit. So I'll start with a primer. Protecting ecosystems. Do environmental protection go both ways? And what is our role in that? So planetary protection is a guiding principle in the design of interplanetary missions, aiming to prevent biological contamination of both the target celestial body and of our Earth in the case of sample return missions. Planetary protection reflects both the unknown nature of the space environment and the desire of the scientific community to preserve the pristine nature of celestial bodies until they can be studied in detail. There are two directions. So forward contamination is the transfer of viable organisms from Earth to another celestial body. So in this image, it's the idea that on Earth, we have imparted some organisms on our spacecraft. And while the spacecraft is in transit and then gets to the planetary surface, transfers some of that organisms onto the celestial body that we're interested in. Backward contamination is the transfer of organisms, if such exists, back to Earth's biosphere. So embedded in that is the assumption that there are extraterrestrial organisms, which you have read a little bit about these past 2 days. And embedded in the assumption is that they survive, their transit back to Earth, and then we then, I guess, contract them or like have to coexist with them. So that's the concern. What could these extraterrestrial organisms be and where are they? So why do we want to avoid forward or backward contamination? Because we want to discover life in space to answer this existential question of, are we alone in this universe? If we were to bring organisms with us to our destinations of interest, we wouldn't be able to disambiguate whether the life was there in the first place or if we brought it. Given that we are discovering more and more planets that have water, we are more and more confident that life could exist and that life could look like organisms on Earth elsewhere in our solar system. Excuse me. The spacecraft that have informed us of the possibility of life and where they could be is in this diagram. Some of these missions are long past, like Voyager, Cassini, and Galileo, which give us basic foundations to the metrics on top, like energy sources, ocean signatures, solvents, and etc. Some spacecraft are in the more recent past, like Dawn, New Horizons, and Cassini. And then some spacecraft are proposed for the future missions, like Europa Clipper and Dragonfly. But this is a very essential question that NASA has, and we've been focusing on this question for many a decade. To expand upon the types of planets, the chemical of the composition of the planetary surfaces biases the kind of microorganisms that may live in these types of environments, and subsequently the kinds of chemicals that we will try to look for. So in each panel, the top is a regular photograph of the sample, and the bottom is a 400 times magnified version of the top image. That's over here. The microorganisms here include species from a range of environments, from the Sonoran Desert in Arizona to the Komori Channel in Palau. And then here on the right is a panel of the different kind of chemical compositions where astrobiological life could possibly exist, not just in icy moons that have water, but also in places that are, say, driven by methane, like Titan. So in the end, we don't really know what life looks like because we haven't found extraterrestrial life, not yet at least. So that's why we need planetary protection, so that that discovery of extraterrestrial life can be unambiguous, clear, and certain. Okay, so that motivates why we have planetary protection. So on the left here is a picture of our Cartoon Mars rover demonstrating how we already prevent the spread of germs in what looks like a pandemic PSA of washing our hands, wearing masks, and maintaining social distance. So many of the planetary protection practices have analogous practices, such as sterilization, personal protective equipment, and physical distance when applicable. On the right, what we see is a table that shows the rigor of planetary protection requirements as it pertains to different types of missions. So what you'll see here is that the types of missions are dictated by biological interest, probability of contamination, type of mission, target body, and then the output is how strict are the requirements. So the range of requirements varies from the most lenient case where we are not interested in the biology of the destination at all. It doesn't matter the probability of contamination, and the target bodies are places that are very hot or desolate, like Mercury, Venus, Moon, Sun, and asteroids. And then they range all the way to the strictest type of planetary protection missions, which are in the case of back contamination, where we don't know what the probability of contamination is, and we're returning samples back to Earth. For forward contamination, the type of the strictest kind of mission would be where the biological interest is very high, the probability of contamination is high. The type of mission is a lander or some planetary surface vehicle where you really get in there. And target bodies examples include Mars and Europa, say Enceladus, Titan, so places like that. Now the question could be, what are or could be the forward contaminants? This could help us understand how strict we need to be when we are designing, building, and integrating our spacecraft to send into space. So this is a reminder that forward contaminants are germs that we bring from Earth to space. These contaminants are typically quite resilient of vacuum and extreme temperatures. The table shown here should look familiar if you read the PPOSS research white book. Vacuum is defined by a low pressure from 10 to the -3 to 10 to the -7 pascals. This typically renders active life and metabolism impossible, but for some bacteria, it's the case where they can survive this. Some long-term space missions prove that inactive anhydrous state microorganisms can survive up to 6 years and probably longer. So this motivates us to be very vigilant and aware that there are some ways that we can contaminate the kind of science that we do based off of the contaminants that we impart on spacecraft when we launch them into space. Some of these bacteria look like over here. I just Googled Bacillus subtilis. This is what it looks like. And then another strain looks like this. And then here's a fan favorite, the tardigrades. You might pronounce it differently than me, but they are also colloquially known as water bears, and they're known for surviving through space, coming back, and being able to come back to life. So kind of cute in a gross way. All right, where are the contaminants? So we were just talking about what the contaminants are when we're building, designing spacecraft. Where could they be imparted onto the spacecraft system? Forward contaminants are introduced onto the spacecraft through ground support equipment, the environment that the spacecraft is being built in, and personnel who are working with the spacecraft. This breakdown here shows even further the types of organisms that survive the clean room microbiome environment and would really mess up astrobiological discoveries on icy moons. These organisms have to be. Yeah, what's up?
I have a question. What if you have like radiation shielding that's lead, and you land on like Titan or whatever, and you give the organisms like lead poisoning or something. Is that a consideration?
Oh, well, I don't really know if we build with lead, but yes, I think that would be a consideration if, and maybe that's why spacecraft aren't built with lead. Okay.
Okay, thank you.
Yeah, no problem. So the organisms that potentially live in a clean room microbiome and we're worried about surviving through space have to have the intersecting characteristics of being desiccation resistant, radiation resistant, halophilic or halotolerant, psychrophilic, and autotrophic. And I had to look some of these words up. Autotrophic means that an organism that produces complex organic compounds uses carbon from simple substances such as carbon dioxide, generally using energy from light or inorganic chemical reactions. Psychrophiles or cryophiles are extremophilic organisms that are capable of growth and reproduction at low temperatures. And halotolerance is tolerance to ionic stress, or the ability of an organism to grow at salt concentrations higher than those required for normal growth. On the right is a flow chart of the contamination source, the mechanism for transfer onto the spacecraft, then the necessary characteristic of the organism to survive space. As you can gather from this diagram, there are many places to introduce organisms, but we've also thought of many ways to mitigate contaminant transfer, and the final organisms have to have a series of unique characteristics to survive. The amount of organisms that contaminate the spacecraft correlates with how much effort and vigilance we retain in building, integrating, and launching the spacecraft. Okay, now let's look at backward contamination. So how do we evaluate risk for returning samples? This is from the COSPAR Planetary Protection Policy document. But in summary, the things that we care about when we're evaluating risk for returning samples is, does the target body have liquid water? Does the body have metabolically useful energy sources or organic matter? Are there extreme temperatures? What is the dose of radiation? And is there a natural influx of material on the target body? To ultimately control for contamination, we need to know certain things. So we need to know contamination knowledge, which is the information gained from studying the collected or curated reference materials. We also need to know engineering knowledge, which is the information gained from engineering models after launch. These are the different mechanisms needed for contamination control to guarantee that we can achieve planetary protection. Okay, how do we control for contamination? To actively control for contamination, we have different methods to mitigate forward contamination and backward contamination. For forward contamination, we make sure to build our spacecraft in clean rooms that filter out dust and other organics. We can wear bunny suits like some of these spacecraft engineers, which contain our own organics. And we can also bake spacecraft, which is something shown in this picture. It's called dry heat sterilization, which is baking the spacecraft at some temperature for some amount of time to kind of sterilize the kind of bacteria or organisms that are on the surface. For backward contamination, we can isolate samples in people like Apollo 11 astronauts. Once we properly monitor and measure for contamination, we can start to loosen our restrictions and then reintroduce them back into our society. Okay, and I'll end with what are or could be the consequences. So the scientific consensus is that the potential for large-scale effects, either through pathogenesis or ecological disruption, is extremely small. Nevertheless, returning samples from Mars will be treated as potentially biohazardous until scientists can determine that the returned samples are safe. The goal is to reduce the probability of release of a Mars particle to less than 1 in a million. It is important to note that contamination of the target itself is also a threat to future scientific objectives. Like we were talking about before, we are really interested in this question of life, so we do not want to contaminate our results. For this reason, there is this chart that represents the possibility of getting a false positive or a false negative, or a true negative or a true positive. So if we have really loose planetary protection laws, then we have a broad ellipse of results. Results can smatter anywhere across this area, and we can get a range of false positives and false negatives that we really don't want. What we really want to do is make our practices very rigorous, very comprehensive, such that we get something like this thin ellipse, where we get results that are constrained to having true negative or true positive results. That is our goal. We're not perfect, so there is a small possibility of getting false positive and false negatives, but this is the result of our efforts in planetary protection to thin this ellipse to get true, pure results. All right. So you should be familiar with this discussion prompt. I can't wait what you have to hear. So during the Apollo missions, the return of lunar samples to Earth was handled with great care to not adversely affect Earth's environment and its inhabitants. Standards were developed. So some questions are, if there is microbial life on Mars or on other solar system bodies that our spacecraft visit, what rights to protection would this microbial life have? Can humans without avail contaminate and forever change pristine planetary environments with life forms or without? And what are planetary protection policies and why do we need them? Okay, just a reminder, listen actively, ask for clarification, do not interrupt. I don't think we had any problems, so I'll just go to the next slide. We're going to follow this framework in our discussion, and let's have a discussion until 2:30.